Hello students, once again welcome back to the chapter called States of Matter. Now in the previous video lecture we talked about very interesting thing, and that was nothing but Z, the compressibility factor, which gives you the extent of deviation of the gas, from its ideal behavior. And we talked about three different conditions of Z value, that is Z lesser than 1. Okay, let me just make this even more broader so that we can write down the points. We talked about this and we talked about this. So Z lesser than 1, Z equal to 1 and Z greater than 1, where I will just write it down over here. Z was nothing but volume real upon volume ideal, where volume ideal is calculated by the formula PV is equals to nRT. Correct? Very simple, very easy. So these are the three conditions we talked about. If Z is lesser than 1, I would say V real is lesser than V ideal. That means whatever volume you are expecting from the ideal gas equation, from that the real volume will be lesser. Now, for example, if you are expecting 10 ml over here from ideal gas equation, then you are getting actually as 8 ml. So V real is lesser than V ideal. Now, when will this happen? When there is more force of attraction between the gaseous particles. Correct? Getting? आप expect कर रहे हो 10 ml, but you are getting 2 ml lesser than the expected volume. So that means the gaseous particles are having force of attraction between each other. Similarly, if Z is equal to 1, then V real is almost equals to V ideal. This is the case where ideal gases come, and in case of ideal gases there is no force of attraction or no force of repulsion. That is what we have seen in kinetic molecular theory of gases. And if Z is greater than 1, that means V real is greater than V ideal. That means your ideal volume is lesser than the volume that you get experimentally. That means if you are getting 10 ml over here from ideal gas equation, then actually when experimentally tested on the same gas at same temperature, you see that the volume you are getting is 12 ml. Let's suppose hypothetical values. So that means over here the force of repulsions are greater than the force of attraction, whereas in the first case force of attraction is greater than the force of repulsion. So I might say that if force of attractions are higher in any gaseous particles, then the compressibility of that gas is going to be easy. Correct? That means, very important point, that means I can easily liquefy that gas because the force of attraction between the particles is very, very high. Whereas in the case of this one, third case, Z greater than 1, force of repulsion is higher than force of attraction. That means the compressibility of the gas is difficult over here. Correct? Compressibility is difficult. And if compressibility is difficult, I would say cannot be easily liquefied. Correct? So this whole thing was proposed by Amagat Andrews that we saw in the last class, and he proposed a graph of Z versus P. To prove this point, he proposed a graph Z versus P. Now what is Z over here? We know Z is equals to P V real by N RT. Correct? P V real by N RT. Now when he started to draw the graph for various gases, understand, the first graph we are going to see over here, Z versus P, we are going to see for different gases at constant temperature. Temperature is going to remain constant. Let's say we are taking this graph at 298 Kelvin, that is nothing but 25 degrees Celsius, standard ambient temperature. So what was observed over here? The observation was that for the gases like hydrogen, for the gases like helium, if this was the ideal case, this should have been the ideal case. Let's suppose over here Z is equals to 1. Then in case of hydrogen and helium, when he increased the pressure, he saw that the graph was showing always a positive deviation, always a positive deviation from their ideal behavior. We are able to see 1 से value ज़्यादा आएगी यहाँ पर. Either the value will be 1.5, 1.6, 1.8, something like that. Correct? And then there were gases like, let me just change the pen, like HCl, NH3, or I would say H2O, water vapors. So these were the gases in which the force of attraction was much higher than the force of repulsion because of the dipole being present. Over here there was no dipole, right? These are non-polar gases. So in the polar gases, what he saw that up till low pressure conditions, the gas was following the ideal behavior, and after certain pressure increase, there was a negative deviation of the gas. Let's suppose this gas is NH3, correct? Up till low pressure, let's say P, low pressure, high temperature conditions, the gases follow ideal behavior. So see, they are following the ideal behavior, and then after a certain amount of pressure, they started to show a negative deviation. Why? This area over here, it denotes that there is force of attraction between the particles. But after this pressure over here, we can see that the deviation is increasing towards the positive side, and they cross the graph, ideal gas graph, and they move towards the positive side. So why does this happen? Because we know that you can bring two particles closer to a certain extent. After that extent, if you just try to push these molecules even more closer, then the force of repulsion will start to dominate over force of attraction. We have done this in chemical bonding, right? Two atoms coming closer, they will come closer to a certain extent. Beyond that, the force of repulsion will start to dominate, correct? So that is what is being observed over here also. But what was the other thing which was being observed? That if one graph was like this, then the second graph was something like this. The third graph was something like this. So what does these depths of the graphs show? This shows that higher the negative value, or I would say lower the value of Z compared to 1, lower the value of Z, more is the difference between V real and V ideal. If Z is lesser than 1, we know that V real is lesser than V ideal, and more the value of Z lesser than 1, more is the difference between V real and V ideal. That means more the force of attraction between the particles, correct? So over here you have to understand that the graph which is having lesser depth compared to the graph which is having higher depth is less compressible compared to the gas which is having higher depth. For example, if this pink graph over here is NH3 and green graph over here is, let's say, CH4, then over here I would say CH4 can be easily liquefied compared to NH3, or CH4 has more better force of attraction compared to NH3. Is that clear? Easy, perfect. So this is what you have to understand. Now this will not be the case in reality because NH3 has hydrogen bonding in between the particles of NH3, whereas CH4 does not. So if I just want to make it a real scenario over here, I would exactly do the opposite of this. I would say the green gas over here is NH3 and the pink gas over here is CH4, because CH4 is less easily liquefied compared to NH3. So this was the graph of Z versus P, first case, that is nothing but different gases at constant temperature. Perfect. Now we are going to see the second case. We are going to see Z versus P for a single gas at variable temperatures. अभी temperature constant था, gases different थी. अब हम gas constant कर देंगे for same gas at different temperatures. We are going to see, and let's see what is the nature of the graph we are getting. Perfect. Chali, let's see the graph. Okay, let's see then the graph of Z versus P at different temperatures but for same gas. Let's suppose that gas is NH3, which shows a negative deviation initially with respect to the ideal behavior, right? With respect to the ideal behavior, this was the ideal behavior, Z is equals to 1. But we are able to see that there are different values of Z over here. See this? This is at temperature. Which temperature? This is at T1. So I would name this as Z1. This is nothing but at temperature T2. I would name it Z2. This is at temperature T3, Z3. This is at temperature T4, Z4. I would name the values of Z like this, where I am telling you T1 is greater than, T1 is lesser than T2, is lesser than T3, is lesser than T4. That means T4 temperature is the highest. और वो होना भी चाहिए था. The nature of the graph proves to the statement that low pressure and high temperature conditions are the conditions for ideal behavior. So any real gas, if the temperature is increased for that gas, you will observe that the negative deviation of that, the deviation of that gas starts to decrease. What happens? With increase in temperature, the deviation starts to decrease. That means real gas tries to come closer to ideal gas behavior, and that is what was observed over here. At temperature T1 the depth was this, at temperature T2 the depth decreased, at T3 it decreased, at T4 it decreased, and if I go beyond T4, let's say T5, you will see graph almost something like this, very close, very close to the ideal behavior, right? So this T5 is the temperature, T5 is the temperature where real gas behaves as ideal gas. Real gas behaves as ideal gas, and this temperature was termed as Boyle's temperature, Boyle's point, Boyle's temperature. Very important, very important. What is Boyle's temperature? The temperature of a real gas at which it starts to behave as ideal gas is termed as Boyle's temperature. क्या बोलते हैं उसको? Boyle's temperature, या फिर कुछ बुक्स में इसको Boyle's point ऐसा भी बोला जाता है. So you have to note down this point. This definition is 100% asked in your 1 marker questions. Very important. So this was very interesting part where we talked about the graph of Z versus P for different gases at constant temperature and for same gas at different temperatures, and with the help of this compressibility factor we can comment on which gas has higher force of attraction and the gas which is easily liquefiable. That is the important point, and from this point your questions will be asked, which will be discussed in your regular class. Till then, please take care of yourself, keep smiling, be positive. wait for the next video to come wherein we are going to derive the real gas equation. Perfect? Till there, take care of yourself. Bye bye.